Welcome! Today, we'll be tackling the problem titled PathSum 3. This is a fascinating problem that lies at the intersection of binary trees and algorithms. We'll explore its requirements and dive into effective approaches to solve it. Let's get started. In this problem, we are tasked with finding the number of paths in a binary tree where the sum of the node values along the path equals a given target sum. A path is defined as any sequence of nodes connected through parent-child relationships. Importantly, the path can start and end at any node within the tree, and it must contain at least one node. The inputs to the problem are the root of the binary tree and the target sum. The root represents the starting point of the tree, and the target sum is the value we are checking for. The output will be the total count of such paths in the tree that satisfy this condition. For example, if the tree is empty, the result would naturally be 0 since there are no paths to evaluate. Let's look at an example to better understand the problem. Consider a binary tree with the following structure. The root node has a value of 10, with two child nodes 5 and -3. Node 5 further has children 3 and 2, while node -3 has a single child, 11. Additionally, node 3 has two children, 3 and -2, and node 2 has one child, 1. Now, if the target sum is 8, the output for this tree would be 3. This is because there are 3 distinct paths in the tree that add up to 8. Specifically, these paths are 5 to 3, 5 to 2 to 1, and -3 to 11. Each of these paths follows the parent-child connections, and their sums match the target value. Here's another example to illustrate the concept. Imagine a binary tree where all nodes form a single straight line leaning to the right. The root node is 1, which is connected to 2, followed by 3, 4, and 5. This tree has no branching, and the target sum is 3. For this setup, the output is 2, because there are two paths that sum to 3. The first path is from node 1 to node 2, and the second path is the single node 3. This example highlights that paths can consist of just one node if its value matches the target sum. To further clarify, for the tree in the previous example, the explanation of the paths is as follows. The path 1 to 2 has a sum of 3, and the single node 3 also equals 3. Now let's consider a different tree structure. In this case, the root node is 1, which has two children, -2 and -3. Node -2 has its own children, 1 and 3, while -3 has a single child, -2. Additionally, node 1 under -2 has a child, -1. If the target sum is -1, the output is 4, as there are 4 distinct paths in the tree that sum to -1. To break down the paths for the tree with a target sum of -1, the first path is from node 1 to -2 to 1 to -1. The second path is from -2 to 1 to -1. The third path is the straight path from node 1 to -2. Finally, the fourth path is the single node -1. These paths demonstrate the flexibility of the problem, as paths can include multiple nodes or just one node as long as the sum matches the target. Moving forward, we must also consider the constraints and special cases that can arise in this problem. The problem comes with some important constraints. First, the tree can have up to 10,000 nodes, so the solution must be efficient to handle large inputs. The values of the nodes and the target sum can range from -1 billion to +1 billion. This means the tree and target can include negative values, which adds complexity to the problem. Additionally, special edge cases include empty trees, where the output should be 0, and trees with a single node, where the result depends on whether the node's value matches the target sum. If no paths in the tree match the target sum, the output should also be 0. Keeping these scenarios in mind is crucial when designing an effective solution. To solve the PathSum 3 problem, let's first consider a brute force approach using a naive recursive DFS strategy. The intuition here is straightforward. We explore all possible paths in the tree by traversing each node and, at every step, calculate the cumulative sum of nodes to check if it matches the target sum. This involves starting a new path at each node, traversing downward in the tree, and summing up all possible subpaths originating from the current node. To implement this, we would use DFS to visit every node, repeatedly calculate the cumulative sums for every potential subpath, and count how many of these paths equal the target sum. However, this brute force approach comes with significant drawbacks. In terms of time complexity, The worst case occurs with a skewed tree, where each node's sums are recalculated multiple times, leading to O(n) squared time complexity. Space complexity is O(h), where h is the height of the tree, due to the recursion stack. While conceptually simple, this method is inefficient for larger trees because of the redundant calculations it involves. To overcome the inefficiencies of the brute force method, we can adopt an optimized approach that uses the prefix sum technique with a hash map. The key intuition here is to avoid recalculating sums for every subpath by leveraging the cumulative sum of the paths from the root to the current node. By storing these cumulative sums in a hash map, we can determine in constant time whether a valid subpath exists. Here's how it works. For a given cumulative sum, cur_sum, if there exists a previous cumulative sum, prev_sum, such that the difference cur_sum, prev_sum equals target sum, then the subpath between these two sums matches the target sum. To implement this, we traverse the tree using DFS, maintaining a running cur_sum and a hash map, prefix sum, to track the frequency of each cumulative sum encountered. At each node, we calculate the current sum and check if the difference, cur_sum target sum, exists in the hash map. If it does, we know a valid subpath exists. Before diving deeper into the tree, we add cur_sum to the hash map and remove it after backtracking. This backtracking ensures that the hash map only reflects the state relevant to the current path. The optimized approach significantly improves efficiency. The time complexity is reduced to O(n), as each node in the tree is visited only once during the DFS traversal. Space complexity is O(h plus n), accounting for the recursion stack, where h is the height of the tree, and the space used by the hash map to store cumulative sums. This approach eliminates redundant calculations, making it highly efficient for larger trees. Additionally, the backtracking mechanism ensures we do not retain unnecessary data in the hash map. Given these advantages, the chosen strategy is the optimized approach using prefix sums with a hash map. This method effectively reduces the time complexity from O(n) squared to O(n), making it suitable for larger datasets. It also strikes a balance between clarity and performance, providing an elegant solution to count subpaths efficiently. While the brute force approach is easier to grasp conceptually, its inefficiency for larger inputs makes the optimized approach the better choice overall. When comparing the two approaches, we can identify clear trade-offs. The brute force method is simple and easy to implement, which makes it appealing for small trees or as a starting point for understanding the problem. However, its major drawback is the poor performance due to redundant calculations, which render it impractical for larger datasets. On the other hand, the optimized approach using a hash map and prefix sums is highly efficient, as it avoids recalculating sums and ensures scalability for larger trees. Its slight increase in implementation complexity is a small price to pay for the significant performance improvements it offers. Given the problem constraints and the need for scalability, the optimized approach is undoubtedly the better choice, offering both efficiency and elegance in solving the path_sum_3 problem. To start, the problem at hand involves determining if there's a root-to-leaf path in a binary tree where the sum of all the node values equals a given target sum. The brute force approach to solve this uses a naive recursive depth-first search, or DFS, to explore all possible paths from the root to the leaves. Here's how it works. As we traverse the tree, we subtract the current node's value from the target sum and check if the remaining value can be fulfilled by the subtree. If we ultimately reach a leaf node and the remaining target sum equals the value of that leaf, then we've found a valid path. This method includes a few key steps. First, there's the base case. If the current node is null, meaning we've gone beyond a valid part of the tree, we stop and return false. Next, if the current node is a leaf, we check if its value matches the remaining target sum. If it does, we return true, otherwise, we return false. These two steps form the foundation of the algorithm, ensuring we handle the simplest cases before diving deeper into the tree structure. Now, for the recursive exploration. At each step, we subtract the current node's value from the target sum to calculate the new target sum for the subtree. Then, we recursively check both the left and right children of the current node using the updated target sum. The results from these recursive calls are combined. If either the left or right child returns true, that indicates a valid path exists somewhere in the subtree, and we propagate this true result back up the call stack. Finally, once all recursive calls complete, the function started at the root will return true if any valid path is found, or false if none exist. This approach leverages the natural traversal behavior of depth-first search, which is well suited for exploring paths from the root to the leaves. By subtracting the node values as we go, we focus only on the amount of target sum that remains to be satisfied, effectively pruning the problem space. The recursive nature of this algorithm also allows us to backtrack easily once we finish examining a path. The binary tree structure supports this approach seamlessly, and the call stack provides a way to track the traversal path without needing additional data structures. Each function call corresponds to a single node, and every node is visited exactly once during the traversal. This makes the time complexity of the algorithm O(n), where n is the total number of nodes in the tree. For space complexity, the maximum depth of the recursion corresponds to the height of the tree. In the worst-case scenario, such as a highly skewed tree, this results in O(h) space usage, where h is the tree's height. There are a few edge cases to consider. If the tree is empty, the algorithm should immediately return false. For a single-node tree, it simply checks if the node's value matches the target sum. Negative values are also handled naturally, as subtraction accommodates them without any special adjustments. While this brute force approach is efficient for smaller trees, further optimizations, such as iterative DFS, could be explored to reduce the reliance on the call stack. To better understand how this works, let's consider a concrete example, starting with the binary tree structure shown here. In this example, the target sum is 22. If we examine the path 5, 4, 11, 2, the sum of these node values equals 22, making it a valid path. The algorithm successfully identifies this and returns true. Here's the Python implementation of the brute force approach. The function begins by checking whether the root is null. If it is, the result is false. Next, it checks if the current node is a leaf by verifying that both the left and right children are null. If it's a leaf, the function compares the node's value with the target sum. If they match, it returns true, otherwise, it returns false. For non-leaf nodes, the algorithm recursively calls itself on the left and right subtrees, each time subtracting the current node's value from the target sum. If either of these recursive calls returns true, that means a valid path has been found. This implementation is compact and elegantly captures the core idea of solving the problem using depth-first search. The implementation aligns perfectly with the algorithmic steps we've discussed, ensuring that all potential paths in the tree are explored while efficiently pruning unnecessary branches. With its simplicity and clarity, this recursive DFS approach provides a solid foundation for tackling the path sum problem, especially for smaller trees or scenarios where recursion depth isn't a limiting factor. This solution is designed to solve the path sum 3 problem using a depth-first search (DFS) approach. The goal is to find all paths in the binary tree where the sum of the node values equals the target sum. Here's a detailed explanation of the code. 1. Tree node class. This is a simple class definition for the binary tree nodes. Each node contains a value val, a left child left, and a right child right. This is the standard structure for a binary tree node. 2. Solution class and pathsum function. The pathsum function is the main method that calculates the number of paths that sum up to the given target sum. It uses a helper function DFS to perform a recursive depth-first search. 3. DFS function. This function is the core recursive logic for traversing the tree and calculating the path sums. Base case, if the current node is null, the function returns 0 because there are no paths to check. Current path sums. For every recursive call, we update the list current path sums. This list keeps track of all path sums ending at the current node. For each previous path sum in the list, we add the current node's value to extend the path. Additionally, we start a new path from the current node by adding its value as a single element list. Count matching paths. We count how many of the current path sums match the target sum using the count method. Recursive calls. We continue the DFS by recursively calling the DFS function for the left and right child nodes, passing the updated current path sums. Return total count. The total count for the current subtree is the sum of matching paths from the current node and its left and right subtrees. 4. Return statement. The pathsum function starts the DFS with the root node and an empty list of path sums. ####key optimizations and complexity. Optimized path tracking. Instead of recomputing sums from scratch for every node, we maintain a running list of path sums, reducing redundant calculations. Complexity: the time complexity is O(n) squared, in the worst case for an unbalanced tree, where n is the number of nodes. In a balanced tree, the complexity is closer to O(n) log n. This solution effectively handles edge cases, such as an empty tree, root is none, or negative values in the tree that may contribute to the target sum. The recursive DFS ensures that all paths are explored while maintaining efficiency. Here, we start by defining the basic structure of a binary tree using a tree-node class. Each node has a value, and references to its left and right child nodes. The constructor allows us to initialize nodes either with just a value or with a value in child nodes. Then, we define the solution class, which contains the main method to solve the problem, pathSum. This method takes the root of the tree and the target sum as inputs. To calculate the number of paths that sum to the target, we call a helper method named DFS, passing the root node, the target sum, and an empty list to keep track of the path sums as we traverse the tree. The DFS method is a recursive helper that explores all potential paths in the tree. If the current node is null, it simply returns 0 as there are no paths to evaluate. Otherwise, we update the list of current path sums by adding the value of the current node to each sum in the existing list, and also include the current node's value as a new starting path. Next, we count how many of these updated path sums are equal to the target sum. This count is then incremented by the results of recursively calling DFS on the left and right child nodes, passing along the updated path sums. Finally, the total count for the current node and its subtrees is returned. This approach ensures we evaluate all paths in the tree efficiently. In this problem, we need to count the number of paths in a binary tree where the sum of the node values equals a given target, called target sum. A key detail here is that the path can start and end at any node within the tree, but it must follow parent-to-child connections. To illustrate this, consider the example tree provided. The root of the tree is 10, and it has two children, 5 on the left and -3 on the right. The left subtree of 5 further expands with nodes 3 and 2, while -3 has a single child 11. Notice that some nodes, such as 3 and -2, are leaf nodes without children. Given the target sum of 8, we'll explore how to identify all paths that meet this condition within this tree structure. We start our solution with a depth-first traversal of the tree, beginning at the root node 10. Here, the current path sums list, which tracks the sums of all ongoing paths, is initialized as empty. At node 10, we update the list to include the current node value, making it 10. Since no path currently sums to 8, the count remains 0. Moving to the left child, node 5, we add its value to all ongoing path sums and start a new path with only 5, resulting in current path sums equals 15, 5. Again, no matches for 8, so the count remains 0. At node 3, the sums are updated to 18, 8, 3, and we now have a match since the path 5, 3 sums to 8. The count is increment to 1. Continuing to the left child, another node 3, the sums become 21, 11, 6, 3. Here, no new paths match the target, and since this node has no children, we return 0 for this branch. From the left leaf node 3, we backtrack to node 3 and explore its right child, node -2. The path sums are updated, and any matching paths are counted similarly. Once the left subtree of node 5 is fully processed, we backtrack again to node 5 and move to its right child, node 2. Here, we repeat the process for the right subtree of 5, including its child node 1. After completing the left subtree of the root node 10, we traverse its right child, node -3, and subsequently its child node 11. By the end of the traversal, we find that there are 3 paths in total that sum to 8, 5, 3, 5, 2, 1, and 10, -3, 11. This gives us the final count of 3 for this example. In a simpler scenario, consider the tree with just a single node 1 and a target sum of 1. Here, the depth-first traversal begins at the root node. The current path sums list is updated to include the value of the node 1. Since this matches the target sum, we increment the count to 1. As there are no children to recurse into, the traversal ends, and we return the count of 1. This demonstrates that even with a single node, the algorithm can correctly identify matching paths. Now, if we take a slightly larger tree with nodes 1, 2, and 3 and set the target sum to 5, we'll see a different outcome. In the tree with root 1 and children 2 and 3, the traversal begins at node 1. Here, the current path sums list is updated to 1, but no paths match the target sum. Moving to the left child, node 2, we update the path sums to 3, 2. Again, no matches are found, and since 2 has no children, we return 0 for this branch. Backtracking to node 1, we proceed to its right child, node 3. The sums are updated to 4, 3, but still, no paths match the target. With no further nodes to explore, the traversal ends, and the total count remains 0. This illustrates that not all trees will contain paths matching the target sum, and the algorithm correctly identifies such cases. To solve this problem efficiently, we rely on a depth-first traversal of the tree while maintaining a rolling list of path sums. At every node, we calculate new path sums by adding the current node's value to all ongoing paths and by starting a new path with just the current node. We then check these sums for matches with the target sum. By recursively exploring both the left and right subtrees, we ensure that every possible path in the tree is evaluated. This approach takes advantage of the tree structure to minimize redundant calculations and provides a systematic way to count all valid paths. It's a concise yet powerful method to address the problem. To analyze the time complexity of our solution, let's start with the depth-first search traversal of the binary tree. Each node in the tree is visited exactly once, which means we perform n recursive calls if there are n nodes in the tree. Next, at each node, we update the current pathsums list by adding the node's value to each existing pathsum. The size of this list depends on the depth of the node. For a node at depth d, the list contains at most d elements, 1 for each ancestor. In the worst-case scenario, such as a skewed tree, the depth is O(n), so updating the list takes O(n) time per node. However, in a perfectly balanced tree, the depth is only O log n, making this update much faster, with a time complexity of O log n per node. Finally, we perform the count operation to check how many sums in the list match the target. This operation iterates over the current pathsums list, and in the worst case, it involves O(n) elements. Combining these steps, we can see how the complexity varies depending on the tree structure. Now, combining the factors we just discussed, the overall time complexity can be calculated. In the worst case, each node performs O(n) work for updating the pathsums and counting, and there are n nodes, leading to a total time complexity of O(n squared). On the other hand, in the best case of a balanced tree, each node performs only O log n work, resulting in a total time complexity of O(n log n). Turning to space complexity, the recursive call stack uses space proportional to the tree's depth. For a skewed tree, the depth is O(n), so the call stack requires O(n) space. For a balanced tree, with depth O log n, the stack space is reduced to O log n. Additionally, the current pathsums list at each node also depends on the tree depth. In the worst case, this list grows to O(n) in size, while in the best case, it's limited to O log n. Together, the space complexity is determined by the larger of these two factors. Thus, the overall space complexity is O(n) in the worst case and O log n in the best case. Comparing this approach to the naive method highlights the efficiency of the optimized solution. A naive approach would compute all possible paths for each node and check their sums, leading to a time complexity of O(n squared for a balanced tree and an even worse O(n cubed for a skewed tree. In contrast, the optimized solution avoids recomputing sums by maintaining a running list of path sums. While it still has a worst-case time complexity of O(n squared, the practical performance is significantly improved due to reduced redundant calculations. To summarize, the best-case time complexity is O(n log n, with space O log n, and the worst-case time complexity is O(n squared, with space O(n). This solution is efficient for balanced trees, though its performance can degrade in highly skewed trees. Now, let's discuss some common mistakes that can occur while solving this problem. First, misunderstanding the base case in a recursive depth-first search is a frequent issue. Many solutions incorrectly handle leaf nodes, which are nodes with no children. Some implementations only check the target sum at internal nodes, rather than ensuring the path reaches a valid leaf node. This is problematic because the problem often requires paths to terminate at leaves, and missing this detail leads to incorrect results. Another common mistake is not resetting state properly during backtracking. For example, if you forget to remove the last node from the current path, it can cause paths to leak into subsequent recursive calls. This results in invalid paths being included in the final solution. Additionally, some people ignore negative numbers, assuming all node values are positive. This can lead to errors, such as summing paths incorrectly or pruning paths prematurely when negative values are involved. It's important to account for both positive and negative node values to avoid excluding valid paths that sum to the target sum. Inefficient traversal is another pitfall, especially when dealing with large trees. Using a brute force approach without pruning unnecessary paths can lead to performance issues. For example, in trees with over 10,000 nodes, the solution may exceed time limits. Optimizing the traversal technique is critical to handle such cases effectively. Poor handling of edge cases is another common challenge. For instance, failing to account for an empty tree or a target sum of 0 can cause runtime errors or incorrect results. Addressing these edge cases proactively ensures robustness. From an interview perspective, this problem often revolves around key patterns, such as tree traversal using DFS or BFS. Mastering recursion and stack-based traversal is essential. Additionally, problems involving paths in trees frequently require backtracking, so being comfortable with this technique is crucial. To optimize, consider strategies like early stopping when the current path sum exceeds the target sum, and minimizing space complexity by avoiding unnecessary storage of paths when only the sum is required. Clear communication is vital when solving this problem in an interview setting. Interviewers often assess how well you articulate your approach, including explaining the recursive base case and addressing edge cases. Demonstrating your thought process clearly can make a big difference. Related problems can also help you build a stronger foundation. For example, LeetCode 112 focuses on determining if a root-to-leaf path exists that matches the target sum, while LeetCode 113 extends this by asking for all such valid paths. The problem at hand, LeetCode 437, differs by counting all paths that sum to the target, not just root-to-leaf paths. Additionally, LeetCode 124 introduces a variation with a different objective, finding the maximum path sum, but shares similar tree traversal techniques. Studying these related problems can help you recognize patterns and prepare for variations of this challenge. There are also alternative approaches to solving this problem. Iterative DFS with a stack is a good option if you want to avoid recursion depth issues, but it requires careful management of the stack to ensure correctness. This approach has a time complexity of O, n, and a space complexity of O, h, where h is the height of the tree. Another option is using BFS with a queue, which tracks nodes and their cumulative sums. This method is often simpler to implement iteratively, but it can use more memory for wide trees. One of the most powerful techniques for path sum 3 variants is prefix sum optimization. This involves using a hash map to store prefix sums, which allows you to compute path sums efficiently. However, this method is only suitable for problems where paths don't need to start at the root. The key takeaway here is that mastering this problem requires a solid grasp of recursion, backtracking, and edge case handling. Recognizing tree traversal patterns and optimizing for large inputs are crucial skills for both solving this problem and succeeding in similar interview questions. Great job! To summarize, we explored an efficient solution to the path sum 3 problem, emphasizing the power of DFS and hash maps. Remember, practicing these techniques will prepare you for similar problems in interviews and real-world applications. Thanks for watching, and don't forget to like and subscribe for more. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!